Suppose you've just made yourself a hot mug of tea. If you forget about it for half an hour, it will cool to room temperature. This is an example of equilibration. More generally, whenever something reaches a steady state and stays close to it afterwards, we say it has equilibrated. In this paper, we ask how long it takes for closed quantum systems to reach equilibrium. More precisely, we look at quantum gases with negligible interactions. This includes systems from condensed matter physics, like the Hubbard model in the free superfluid regime, or Luttinger liquids. But it also includes gases of bosons or fermions confined in boxes. When discussing equilibration, it's important to be clear about what measurements we can do in practice. Returning to our cup of tea, we could see it equilibrating by measuring its temperature with a thermometer. But if we could accurately measure each molecule individually, we would see that the state is constantly changing. In this paper, we look at two classes of measurements. The first are coarse-grained measurements, like particle number or magnetization in a region of space. The second are few-mode measurements, like correlation functions or phase correlators. The next step was to look at some examples. One of these involved n fermions trapped in one half of a box. At time 0, a partition is removed and the gas is allowed to expand. By focusing on the observable that measures the number of fermions in the left half of the box, we can ask whether equilibration occurs and how long it takes. The plot here shows fluctuations of the particle number on the left from its equilibrium value. Even for 15 fermions, these are already quite small. For systems with larger and larger numbers of fermions, these fluctuations become smaller and smaller. Furthermore, the equilibration timescale decreases as the number of fermions grows. Aside from the examples, there are also some more general results. For n-particle systems and coarse-grained measurements, the equilibration timescale is often at most polynomial in n. Also, for few-mode measurements on lattice systems, the equilibration timescale is often at most linear in the number of lattice sites. For one-dimensional lattices, this is actually the best we can hope for. This is because the time it takes for information to propagate along a line is proportional to its length. These timescale bounds are much better than previous more general results, which were typically exponential in the system size. For more details, see the full paper.